Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So, we are continuing with our discussion on the NPTEL online course Combustion of Solid Fuels and Propellants, and we are going to continue our discussion on the module solid propellant rocket. So, if you recall what we introduced in the last class, we have just discussed about the various components of a solid propellant rocket, and we brought our attention mainly to the propellant grain. If you look at the white color stuff inside, which is the propellant grain perforation, and the gray color stuff, which is the propellant grain. So, the perforation is nothing but the internal hollow space, which is called grain configuration. So, we will come to some of the discussions about the grain and grain configuration. So, the various components I think we already discussed, rather we can say we have already revised some of the things, because many of you have already learned the basics of liquid propellant rocket, solid propellant rocket. So, there is no point of discussing those things again, but few things we cannot avoid revising, because the focus of the course is combustion of solid fuels and propellants, but without knowing that what kind of solid fuels we are talking about and where it is actually going to be applicable, that is why we want to just bring some of the basic stuff for solid propellant grain. So, as we now know that propellant is a combination of fuel and oxidizer, and they are made into a solid block of material, which is known as the propellant grain. So, this propellant grain is stored in the or placed in the interior of the motor casing. So, the outer casing, you can see this is the outer casing of the motor. So, it is placed internally in the motor casing. Now, depending on the perforation, which is basically the grain configuration as per the rocket terminology. So, based on the perforation, the burning rate is going to be different. Now, this burning can be like either increasing with time, it may decrease with time, it may remain constant with time. That depends on like what are the internal perforations used in the grain. Now, here it is shown that only single grain, but there may be possible that two or multiple grains are placed together in order to maintain a different thrust time profile. So, with time the thrust is going to change once we have a different configuration. So, now let us look at what is grain and what is grain configuration. We will just discuss briefly before we proceed further. So, as we said, the propellant grain is the shaped mass which is cured from the ingredients. The propellant ingredients basically contain the fuel, oxidizer, binder, and of course, several other ingredients. We will talk about those ingredients after this module. So, if we look at the grain, now categorically the grain can be placed directly into the motor, like either we can make the grain separately in a processing setup, and we can put the cured grain inside the motor casing, or rather we can say we can load the grain inside the motor casing, or we can directly cast the grain within the motor casing itself. So, based on these methods of holding the grain, they are categorized into two type of grains. One is called cartridge loaded grain, sometimes it is also termed as freestanding grain. Like if you can look at, the grain is actually processed and cured separately, not inside the motor casing. After curing, the propellant grain is loaded into the casing, and there are a lot of supports. You can see forward support, backward support, insulations, liners, those are required in order to hold the grain. But the advantage is that if there are issues with any grain, we can easily change this grain, we can replace the grain, because the grains are manufactured or processed separately. But in case of a case bonded grain, grain is processed directly into the motor casing itself. I mean to say that the propellant ingredients are actually mixed and poured directly into the motor casing, and the casting process takes place within the motor casing itself. So, the whole process of casting and curing is done within the motor casing itself. So, of course, compared to the cartridge loaded grain, the fewer inert mass is required in order to hold the grain, because since we are directly casting and curing the propellant within the motor casing, the requirement of the support materials will be less. So, generally small tactical missiles where the mass of the grain is smaller, the cartridge loaded grains are very common, whereas for a big rocket, or rather very huge rocket where the size of the propellant grain is huge, there cartridge loaded grain is not the right way of doing it, because handling that large grain is going to be a difficult task, like loading it to the motor casing. Rather, the grain is processed and cured within the motor casing itself. The grain is cast and cured within the motor casing itself. So, many large rockets use this process of having the case bonded grain. Having said that, now let us look at some of the important terminologies related to the grain and the grain configuration, because you see what we are trying to understand in this course is we will try to focus on how the propellant in the grain is going to burn, what are the underlying mechanisms that the propellant is going to burn. Now, the propellant may contain like various type of ingredients. For example, it will have fuel, it will have binder, it will have oxidizers. They have multiple type of oxidizers, there may be various type of fuels can be applicable. So, how their ingredients are actually going to play a role in the burning mechanisms. So, before trying to understand the burning mechanism, we must know that for what type of fuel, what type of ingredients are we looking for, and where they are applicable. So, the propellant and fuel we are talking about in this course are actually going to be applicable for solid rocket only. So, in this course our discussion is limited to solid rocket only. That is why we are focusing more on revising some of the stuffs related to the solid rocket only. All right. Moving forward, we may look at some of the terminology which are essential for solid propellant rocket. For example, like we said the grain already, that the shaped mass containing the propellant which is placed inside the motor casing, that is the grain. Now, we also said the grain configuration. Now, grain configuration is the basically the internal perforation which we give to the grain in order to have different type of thrust time profile or pressure time profile. So, if you look at the cavity inside the grain, it may have like a cylindrical one like. So, configuration means we are talking about the internal configuration. So, this is the cylindrical one. If you look at the other view of it, it is just a circular cross section. It may have a different type of configuration. For example, it may have like, let us say it will have some square configuration. So, internal perforation is square. So, if you look at the other view of it, it will show a square shape. it may have like star shape, it may have some wagon wheel, like this, it may have like multiple cylindrical holes. So, multiport geometry. So, the internal geometry of the grain is called the grain configuration. So, depending on the configuration, the pressure time or the thrust time profile will change. So, based on the configuration, it may have like the progressive profile, burning profile, or it may have like regressive, or it may have the neutral. As the name suggests, progressive means it increases with time. So, if you just simply plot the pressure or the thrust, with time, we will see that the pressure or thrust is going to increase with time, like this. So, this is the progressive pattern. So, if you look at the cylindrical cross section, cylindrical grain or cylindrical grain configuration, you may see that from the initial burning surface area, as the time proceeds, we can see it will reach to a burning surface like this at a different time instance. It will keep on going as time proceeds, until it reaches to the outer, until it reaches to the final diameter of the grain, or the up to the internal liner of the motor casing. Okay. So, here we can see the burning surface. So, this is the, let us say this is the initial burning surface area ABI, that will go up to the final burning surface area here, which is like ABF. So, it is keep on increasing. If you look at, if you consider the length here, that the length of the grain is L, we can find out the initial burning surface area by considering if the diameter of the initial diameter of the grain was di, if the final diameter is df, we can write down, or we can just symbolize it with small 1. Di is the initial diameter of the grain, df is the final diameter of the grain. So, our ABI is going to be equal to pi di into L, because you have to think about the cross sectional area of the internal surface of the grain. So, if you look at the cutaway view of it, you can see this is essentially the grain. So, here we are talking about the internal surface. So, initial surface was like this, this is the half of this. So, if the length is L there, this was like diameter was pi, di. So, pi di into L, that will. So, basically pi di is going to give us the perimeter of this circle into the length of the grain, will give me the burning surface area. So, the initial burning surface area is going to be ABI equal to pi di into L. Similarly, the final burning surface area will be pi df into L. So, as you can see, as time proceeds, the burning surface area is increasing. As a consequence, the pressure and or the thrust both will increase. So, this type of burning profile is known as the progressive burning profile or progressive burning. Now, if the burning decreases with time, we can say the burning features is kind of regressive. So, this type of burning is called regressive. So, if there are some geometry where we can see that the area is decreasing, we can take one example like let us say rod type of configuration. So, the grain is, instead of having the internal perforation, the grain itself is a cylinder. So, what is going to happen? It is going to radially inward burning. So, in case of a cylindrical perforation, we can say it is a radially outward burning. So, burning is taking place radially outward. So, there we have seen that it is increasing the surface area, but here the surface area is going to decrease. So, this type of burning will cause the decrease in pressure or thrust with respect to time, and that type of burning profile is called regressive burning profile. Now, if the burning area remain constant over time, we can say it is going to be neutral burning, that the burning surface area is remaining constant with time. Similarly, the pressure and thrust will remain constant over time. That type of burning profile is called the neutral burning profile. Now, typical example we can say it is going to be like N burning rocket, where the grain is having the constant area. So, this is the grain of the rocket. So, this is propellant grain. Now, burning is going to take place longitudinally. As time passes, the burning surface area will still remain constant over time. So, this type of profile we can get a neutral burning profile, or we can say in consequence that pressure and thrust will not change with time. So, it will have a constant pressure or constant thrust profile over a time. So, this type of N burning configuration will give the neutral burning profile, but in a combination of two different grain configuration can also give this thing. So, instead of having this the N burning profile, we can have like combination of the rod and tube. We can have two different grain, one will have like cylindrical, other will have the rod. So, we can have in this grain we will have radially outward burning, whereas the rod one will have radially inward burning. So, somehow they may compensate each other and it is going to create a neutral type of burning profile. So, this is possible. It is not only that N burning type of burning can only give the neutral burning, or N burning propellant can only give the neutral burning, but there is a possibility that combination of two different grain configuration can also give us the neutral burning. There is a possibility that making the star shaped grain, choosing the number of vertices and the angle between the plane surfaces, there is a possibility that we can make the configuration in such a way it can also give neutral type of burning. So, of course, in connection with the solid propellant rocket, we should know these terminologies like what is grain, what is grain configuration, what are the different type of grain configuration. Now, generally the radial burning, radially outward or radially inward, or even longitudinal burning, although the propellant grain is 3 dimensional, but generally this type of burning are considered, this type of grains are considered to be 2 dimensional grain, because the burning is taking place either longitudinally or radially. It can be like radially inward or it can be radially outward in case of progressive burning. But there are certain grains where the combination of longitudinal and radial burnings are also possible. There are kind of grain configurations which are having like 3 dimensional nature, you can say. So, those are called 3 dimensional grain. We will show you some pictures later part of this lecture. Okay. Now, let us talk about the various other terminologies which are important in case of solid rocket. What is sliver? Sliver is the unburned propellant. So, remaining propellant which is unburned is called sliver. If you look at certain grain geometry, for example, like cylindrical one, cylindrical grain configuration, the burning will continue till the burning surface reaches to the final diameter of the grain or the till up to the liner of the rocket inside the motor casing. So, here the chance of unburned propellant is very unlikely, but let us say if we have a grain configuration something like a square type, initial burning surface area is a square type. Now, if we keep on generating the burning profile, we will see the corner will become kind of a circular here, rounded shape, corner will not stay as corner. So, it will be circular shape. So, it will keep on continue like this until it reaches to the final diameter. So, it will come like this, like this, like this, like this. So, there is a chance that some amount of propellant will remain unburned after the burning of the main part of the propellant. So, that unburned propellant is called sliver. So, there are some grain configurations where there is a chance of unburned propellant remain, which is of course not expected, and of course, it is undesirable, because this is not going to give us the correct required thrust time profile what the grain is designed for. Because let us say if this is designed for a particular thrust time profile, but once there is a unburned propellant, that will, if the temperature and pressure is high enough, the sliver will also start burning, but that will cause some kind of a different thrust time profile, which is undesirable. So, of course, sliver is necessarily not to be present in the case of burning of the propellant. So, but of course, there is a chance that some mass will remain unburned, which is called sliver. So, this is another terminology. Now, in connection with the burning of the propellant, there are some time which we generally define in case of solid propellant rocket. Like if we again draw the thrust time profile or pressure time profile. So, P or F with respect to time, we generally get a profile like this. So, this is the initial maximum value, either thrust or pressure. Sometime as per the literature, the 10% of the P max. So, let us say this is the 10% of the P max, and if you just join this with here, we will get 2 points. So, this 10% of this P max will get some time duration. This time duration is known as the accent time, TA. It is termed as the accent time. And from here to the, if we draw the aft tangent bisector, like we can see the pressure is increasing and then it is remaining for some time if it is a neutral type of burning, and it is going to tail off or is going to drop. So, if you draw the tangent here, aft tangent bisector we can get, there is some point we will get. So, we can draw normal here. So, this will give us some point. So, from the 10% of the P max till this point is defined, this time period is defined as the burning time. So, this is like up tangent bisector. If you follow any rocket propulsion book, I think this type of terminology will be available there also. So, you please revise that, it is called burning time. Okay. So, I think this terminology also are required to be aware of, because they are very much common in case of solid propellant rocket. Now, there are other terminologies which are very often used in defining certain things in the design of the rocket. So, like wave fraction, wave thickness, volumetric loading. So, we can just look at some of other things like what is the wave thickness. Now, wave thickness is defined as the minimum thickness of the grain from the initial burning surface to the insulated case wall. So, if we just look at our typical cylindrical grain. So, what was our initial burning surface area was this. So, from the initial burning surface to the insulated wall. So, this was the insulated case wall, let us say. So, if we just from here, if we get the distance, this is known as the wave thickness or B. So, this is the minimum thickness of the grain from the initial burning surface area to the insulated case, to the insulated casing or insulated case wall. For different configuration, we can actually define this one in the same way. Let us say if it is a square configuration. So, the wave thickness for the square configuration will be the minimum thickness of the grain. So, from this corner to the insulated case wall will be my wave thickness. Okay. For other combination of grain configuration, it can be to the intersection of another burning surface. So, if there is a combination of two different type of configurations. So, it can be the intersection of the another grain. So, that is defined as the wave thickness. So, this is also very important in terms of burning of the solid propellant. Then we define wave fraction, which is symbolized as Bf, that is defined as the wave thickness divided by the radius of the grain, or we can just write in terms of 2b by the diameter of the grain. Another terminology is called volumetric loading. It has the symbol Vf, which is the propellant volume divided by the chamber volume. Chamber volume means the volume available for propellant, not only propellant, insulation and restrictors till the convergence section of the geometry, or we can say the volume volume of the propellant to the volume available in the chamber for the propellant, insulation, restrictors. So, it is like the total volume we can say. So, this is the volumetric loading fraction. Now, volumetric loading fraction, it is not only volumetric loading fraction or Vf. So, why it is important? Because the aerospace vehicle or the rockets are volume limited. So, the available volume for the propellant is actually limited. We cannot really have abundant space to load the propellant. That is why the density is kind of playing an important role there. Denser the propellant, more mass we can actually put in a constant volume, in a restricted volume. That is why we need to increase the volumetric loading somehow by improve the volumetric loading, so that we can see the volume of the propellant we can know, and we have to use this volumetric loading fraction efficiently, because once the volumetric loading fraction is defined, we know the how much propellant volume is available there. So, we have to use that volume of the propellant judiciously by considering the high dense propellant, and we can actually improve the volumetric loading fraction. Okay. Now, for designing of the various grain configuration, of course, there are various parameters which play an important role there. For example, like flight mission, that will tell us like the rocket motor requirements, the grain geometry, which is very much related to the pressure time or thrust time profile, because what kind of profile we are looking for, is it a neutral one or a progressive or regressive, that will tell us what type of configuration the grain is supposed to be. Now, if it is a complex type of grain configuration, we need to look for that whether the available propellants or the choice of ingredients, can it handle that type of grain geometry. That is another important consideration, because your propellants would have enough strength to handle that type of complex geometry. The generally like it is the propellant is chosen or selected on the basis of the propellant characteristic. For example, like characteristic velocity, the mechanical properties of the propellant, or the grain or the strength of the propellant, the ballistic property like burning rate. So, they are supposed to be well known before we really consider a propellant for the particular applications. So, we can say these are like interrelated requirement for choosing the particular grain geometry. It is not a single requirement that it is fulfilling only the ballistic property or the mechanical property or the burning type of burning or the burning profile, like whether regressive, progressive or neutral. It of course, it depending on the various various requirements starting from the flight mission, because flight mission is going to tell us that what type of what are the rocket motor requirements, and of course, they have to be defined before the grain can be designed. So, choice will very much depending on the interrelated requirements. Okay, so, I think we pretty much covered the terminologies required for us to know the grain and grain configuration. With that, I think we can close this lecture. In the upcoming lecture, we will go little further regarding the choice of grain configurations. We will try to discuss some of the basic configurations like cylindrical grain, square grain, and maybe the star shaped grain. Okay. All right. Thank you.